As we continue our discussion of solutes, I wanted to just give you this slide just to tie a few things together that we have or will talk about. We talk about molecules and this word moles and things like that. So molecular mass is the sum of all the masses of all the atoms in a molecule. So you add up all the molecular masses, okay? And you can use that then to make solutions of certain concentrations. So numbers of molecules are usually measured in moles, this unit called a mole. And 1 mole is equal to 6.02 times 10 to the 23rd molecules. Okay, that's a big number. This ties into Avogadro's number, and the unit Dalton were defined. Both of these things were defined so that 6.02 times 10 to the 23rd molecules is equal to 1 gram. So when you're in chemistry and you're making various molecular concentrations, you'll know how many grams of various things to measure out to make certain concentrations of a solution. And I'm not going to go down that road today, but I would like you to know that a mole is 6.02 times 10 to the 23rd, and I'll let you worry about how to make various molar concentrations, because a mole is a unit of, like in lab we might say make a 5 molar concentration of sodium, or of sodium chloride or something. And so you can use your knowledge of the molecular mass of sodium and of chloride and then figure out how much to weigh out and how much water to mix to make a 5 molar solution. We're not going to do that today though. So molarity, like I drew up here, this M, molarity, not to be confused with meters, is the number of moles of solute per liter of solution. So it's moles per liter in a solution, and it's often used as a concentration. It's a concentration of solution. Okay, I just wanted to point that out. That ties in with water and dilutions and things, and you may see molar solutions measured out. I want you to have some idea what we're talking about when you see that. Okay, one other thing I want to mention, pH. I think that's about it for the water chapter then. So here we have 2 water molecules, and water naturally will disassociate, meaning hydrogens will break off every once in a while and move and form this thing. This is H3O plus. This is called hydronium, and that makes the other one a hydroxide. And this naturally happens in a glass of water. It just happens, and then and it's reversible. That's what these backwards arrow means. These reactions can go either direction. Most reactions are reversible given certain circumstances anyway. So this happens naturally in a glass of water. Now I just want to show you, rather when we write this out and talk about it, rather than writing hydronium over and over again, we usually just talk about the hydrogen that broke off. Okay, so we often just talk about the H plus rather than the hydronium, and we'll talk about OH, right? We'll talk about those two things. But in reality, the hydrogen ions don't just stay hanging out by themselves. They stick to water, forming hydronium. But in a glass of water, dissociation takes place, meaning hydrogens break off at a pretty predictable rate. So the concentration of hydrogen ions in a glass of water would be this, 0.0000007 molar. That would be the concentration. Or, to make it easier, 1.1 times 10 to the negative 7th molarity there, right? So that's moles per liter. That's how common this occurs. And we can convert that to a unit I know you've heard of called pH by taking this exponent, multiplying it by -1, and you get pH of 7. A pH of 7 is neutral. That's what normally happens in a glass of water. Okay? Now, if we add something to this water to increase the hydrogen ion concentration, we make the hydrogen ion concentration go up, right? That's going to, so if hydrogen ion concentration goes up, that is going to cause the pH to become more acidic. So if something donates hydrogen ions to the solution, it becomes more acidic. And I should say, technically, then the pH goes down. So 1 times 10 to the negative fifth molar hydrogen ion concentration, that's higher than 1 times 10 to the negative seventh, right? Because these are negative exponents. So hopefully you know how exponents work. 1 times 10 to the negative fifth would be moving this decimal point over to the right, right? So if we add hydrogen ions, we become more acidic. If we add OHs, right, or we add something that pulls hydrogen ions out of the solution, we become more basic. And notice what happens to pH then. So neutral is a pH of 7, or 1 times 10 to the negative seventh hydrogen ion concentrations. Basic is 1 times 10 to the negative, like super basic is 1 times 10 to the negative 14 hydrogen ion concentrations. That would mean there's 14 leading zeros here. That would be a really tiny amount of hydrogen ions floating around. And what's kind of cool is when you look at pH, at neutral pH, the concentration of hydrogen ions equals the concentration of hydroxide ions. And what's handy about that is you can always calculate how much hydrogen there is and how much hydroxide there is in that solution. So let's say we have something with a pH of, I don't know, 3. So we would know that the hydrogen ion concentration is 1 times 10 to the negative third. And you figure out what plus 3 equals 14. So that would be what, 11? So that would be 1 times 10 to the negative 11th hydroxide concentration in that glass of water. So this is the concentration of hydrogen. This is the concentration of hydroxide. So if you know one of the numbers, it added to the other absolute value, calculating up to 14, lets you know the concentration of the other one. So at a pH of 7, they both have a concentration of 1 times 10 to the negative 7. So the pH scale works this way. It's kind of weird, right? It's logarithmic, which is another important thing to understand. Because it's based on moving a decimal place, it's logarithmic. A logarithmic scale is based on powers of 10 usually. So for example, if we have a pH of 7 and we go to a pH of 6, that is a 10 times increase in the amount of hydrogen ion concentration. If we go from a pH of 7 to a pH of 5, that is a 100 times increase in the hydrogen ion concentration because we went from 10 times 10. And so there you go. So if we look at this scale, this shows you that relationship between OH concentration and hydrogen ion concentration. So at neutral pH, they're equal, and they show a beaker showing this. In an acidic solution, you have more hydrogen ions than you have hydroxide ions. So a pH of 1, like battery acid, right? A pH of 2, your stomach acid. So those are pHs of 1 times 10 to the negative 2 hydrogen ion concentrations in that liquid. As we go more basic, so as we increase our pH, as we increase pH, we become more basic, and hydrogen ion concentration goes down, hydroxide ion concentration goes up. So something like bleach has a hydrogen ion concentration of 1 times 10 to the negative 13th. So if that were the case, what would the OH concentration be? I bet you can answer that. Another thing I want to mention then is that in biological systems such as our blood, where we have acids and bases reacting, we have to maintain a pH, and we do that with a buffer. And a buffer is something that helps maintain pH. Okay? So to give you an example, the one that's common in our blood is the bicarbonate buffer system here. So we have carbon dioxide that we generate through cellular respiration, and it is in our blood. This is how we carry it to our lungs to get rid of it. And when it interacts with water in our blood, it forms carbonic acid, which is a weak acid. Okay, there's carbonic acid, H2CO3. Now, that acid, right now, it has not changed the pH of the blood. But if it ionizes and that hydrogen pops off of it, now it has decreased the pH of the blood, meaning it's become more acidic, right? Now, why is this a buffer? Well, let's say you eat, I don't know, something very acidic. Or something causes your blood to become more acidic. So you have a bunch of hydrogen ions showing up in your blood. Well, if you have a bunch of hydrogen ions showing up in their blood, this reaction is reversible. They'll stick back to each other, forming this molecule again, and this could even go back to these molecules again. So if you have too many hydrogen ions in your blood, the buffer will grab them and it will shift this equation to the left. If, on the other hand, you have a lot of OHs hanging out, a lot of hydroxides hanging out in your blood, and your pH is increasing, it's becoming too basic, then this can disassociate in greater numbers, and it will shift to the right, and it will release more hydrogen ions. And so this buffer system is able to maintain a pH close to, I think, well, near neutral, where we want it, or where homeostasis is like 7.3, 7.4, something like that, where the blood likes to maintain pH. And this buffer system allows us to maintain that pH within a very small range. If our blood became too acidic or too basic, we would die. This is why things like alkaline water are stupid. They don't really help you. They're not really healthy for you because you're just going to neutralize it when you drink it anyway, right? Because we have this system that keeps our blood in homeostasis at the right pH, by either releasing hydrogen ions when things become too basic, or pulling in hydrogen ions when things become too acidic. And you can read a little more about that in your book, but I think that about wraps it up for the lecture on basic chemistry and water. So the next set of lectures that we will watch will be on the major molecules that make up life, those organic molecules, and we'll do that next time.